This lecture will describe what an electric field is and how it exerts forces on charges. The electric field can be imagined as kind of an imaginary force field around any charged particle. So imagine that you had a charge Q in space. In this diagram, it's at the origin of the XY axis. If you were to put any positive charge, called a test charge, Q naught, near it, that positive test charge, whether it's really close to it or really far away from it, would be repulsed from it. It would experience a force away from it. Even if you took away Q naught, there would still be this potential to exert forces on other charged particles. So the electric field is defined as it's in the direction of the force on a positive charged particle near the particle that's creating it. So if I take Q, which is positive, and I think about what would happen if a positive test charge came near it, the positive test charge would be repulsed. So the electric field is drawn as a line away from Q. Q naught would be an imaginary test charge. So the field is a measure of how much force each coulomb of that charge feels. So it would be calculated by finding the electrostatic force between Q and Q naught and dividing it by Q naught so that you could get units of newtons per coulomb. If you wanted to know the force on that charge, then you would just take that charge and multiply it by the strength of the electric field. The direction of the electric field is always away from positive towards negative. So in this diagram, the arrows are pointing to the west. So south is on the west side of the slide, and, to the east. South is pointing towards the east, and west is where the positive side of the field is. Those the fields always point from positive to negative. If I put a positive test charge in the field, it will feel a force parallel to the field lines because it will be pushed in that direction. But if I put a negative charge in the field, it'll move opposite the field lines but parallel to them. Example 1. A 40 microcoulomb charge exists in space. What is the magnitude and the direction of the electric field 3 millimeters from the charge? So plugging into our formula, Fe over Q, and substituting in for Fe, K times the Q that's producing the field times the test charge, little q, all over r squared, and then dividing it by the test charge again, shows us that the field is independent of a charge at that location of 3 millimeters. It is only dependent on the charge that is producing the field, in this case 40 microcoulombs. If I plug in, I get 8.99 e to the 9 newtons meter squared over coulomb squared times 40 e to the negative 6 coulombs divided by 0.003 meters squared. Now remember that our units need to be in coulombs and meters. So if you are in microcoulombs, you need to convert that to coulombs, and if you are in millimeters, you need to convert that to meters. Our answer is 3.2 newtons per coulomb. Electric field is a vector quantity, so if you had several charges acting on a point in space, the total electric field would be the vector sum of those electric fields. So Q1 would exert an electric field and Q2 would exert an electric field, which you could find using the electric field equation and then resolve it into this x and y components, add up the x's, add up the y's, and you'll get the net electric field. Electric field lines are a convenient way to visualize the electric field. Few things to remember. 1. electric field lines point in the direction of the field vector at every point. So in other words, if the field is if it's a positive charge, they'll point away from the charge. If it's a negative charge, they'll be pointing towards the charge. The field starts at positive and ends at negative. And the more dense the field lines are, the stronger the field. So for example, positive Q here has field lines radiating out perpendicular to its surface, away from it. Notice that as you get further from the field, they get further apart because the field gets weaker. If you have a charge that is twice the magnitude, then you'll have twice as many field lines because it's a stronger field. In the second case, we have a negative charge. So it has twice as many field lines, but they're pointing towards the charge because they're negative. What happens when you have multiple charges? Well, let's look at a positive Q and a negative Q. The field lines always are drawn perpendicular to the charge's surface. So in the middle, we get a straight horizontal line pointing from positive to negative. And in order to get the field lines to hit the charge's surfaces perpendicular, then we have to kind of curve things. So you see, you get kind of interesting patterns when you have different amounts of charge or different polarities. But remember, the lines always point from positive to negative. In a parallel plate capacitor, the field line is uniform. I can tell that because the field lines are equally spaced. So the field doesn't really change with distance. And since in a conductor, the charges, the static charge would only build up on the surface, as we discussed in the previous video, you can kind of think of this conductor as acting like as a charged particle. It would have a field around it as well. Insulators, when they build up charge, the charge is built up uniformly, like in figure B. But what if you have like a ring, a conductive ring? So, or like a sphere that's hollow. So remember that the charge only builds up on the surface of the conductor. So in this case, you see that you have a charge inside the conductor, and you have the field lines coming from positive Q, right, coming away from positive Q, radiating out. At the same time, you have the charge on the conductor. The charge on the conductor is going to orient itself so that the negatives are attracted to the interior positive charge, and the positives are going to be along the outside because they're repulsed by that interior positive charge. So what happens is you have more lines going out of the surface, the hollow surface, than you do coming in. And so that means that a charge could actually make its way in. But if there were no charge inside of it, there would be no pathway for the charge to move, and you would be safe in it. It's called a Faraday cage. And this is why we use hollow conductive material to protect our electronics in our computers, etc. Also, remember, the electric field lines are always perpendicular to the surface of a conductor. If it weren't, the charges would move along the surface. And if the surface has a sharp point, you would have an accumulation of more charge, so the field lines would be grouped tighter and the field would be stronger at that point.